Okay, class, today we're going to be talking about section 4.7, which is on LHopitals Rule. Okay, and this is basically the last example of derivatives we'll be looking at, the last application, that is, before we move on to integration. Basically, LHopitals Rule is a way to help us calculate limits, types of limits we weren't able to do before, but now using the derivative can actually help us calculate them. Now this, you gotta be careful how you use this. This can't show up in the early section because you need limits to get derivatives, and now we're using derivatives to help calculate limits. So it can be a little circular if you're not careful about it. But if you already have derivatives developed, this rule can actually really help simplify certain limit problems, and actually will allow us to calculate limits that we couldn't do before. So, for example, let's say we have the limit as x goes to, let's say 1 of x squared minus 1 all over x minus 1. Right? And this is a 0 over 0 case. Simply, you put in 1, you get 0 on the top, you get 0 on the bottom. So since this is a 0 over 0 case, you factor the top and the bottom, and this is something that factors, so we can factor and cancel, and we get the limit as x goes to 1 of x plus 1. And now we can just plug in the value and get 2. Okay. Right, the problem with this method is that, well, it depends on things that can factor, or that we can take the conjugate of, but it won't always work. For example, what do we do if we have the limit as x goes to 1 of, let's say, the natural log of x over x minus 1? Right? This is still a 0 over 0 case, right? Because the natural log of 0 is 0. Or, excuse me, natural log of 1 is 0. And when I plug in 1, I get 0 over 0. So this is a 0 over 0 case. But I can't factor this, right? I can't factor the natural log of x. I can't factor the denominator. I can't use a conjugating factor. If I tried, I wouldn't really get anything useful out. This won't factor. And so this is where LHopitals Rule comes in. All right, so let's give LHopitals Rule quickly. Okay, here's LHopitals Rule. This first bit is just some introductory things, but basically if we have f and g are differentiable on an open interval I, containing a, with g prime of x not equal to 0 on I when x is not equal to a. Okay, so this is just, let's assume everything is working the way we want it to. F and g are differentiable, so we can take their derivatives. And we basically don't want g prime of 0, or g prime of x to be 0 when a on this interval, like identically, okay? But basically, the important part is that if all this crap is true, then if we have that the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x, and they're both equal to 0, then this limit here, the limit as x goes to a of f of x over g of x. Now, since both of these limits go to 0, this is a 0 over 0 case. Okay, if the functions are differentiable and all that, then the limit, this limit is equal to this limit, which is the limit as x goes to a of f prime of x over g prime of x. Okay, so what LHopitals Rule basically says, if you have a 0 over 0 case, then if you're actually able to take the derivative of the top and the bottom, then you can do so to get the same limit out. That this limit will be equal to this limit, which is just the derivative of the top over the derivative of the bottom. Okay, and we can also extend it This is also true of x going to a. If that limit is replaced with like a one-sided limit, like an a plus or a minus, and also true if the limit is going to plus or minus infinity. It's also true, okay, for the limit as x going to a of f of x is equal to plus or minus infinity, and if that's true for g as well. Okay. So the L'Hopital's rule can apply to these indeterminate forms. You've probably heard me use that phrase before, indeterminate. Indeterminate forms, if I'm spelling that right, which is 0 over 0 and infinity over infinity. So if you get a 0 over 0 case or an infinity over infinity case, what L'Hopital's rule says is that provided you can, if you can take the derivative of the top and the bottom, then instead of taking this limit, you can take this limit, which is the limit of f prime over g prime. Alright, so let's go back to that example that gave us a problem earlier. Alright, we had the limit as x goes to 1 of natural log of x over x minus 1. Okay, and this was a 0 over 0 case. Alright, so since this is a 0 over 0 case, we can use L'Hopital's rule. Okay, and what L'Hopital's rule basically says, and I was always taught to write an h over the equal sign, to just let everybody know that we're using L'Hopital's rule. I would appreciate if everyone else would do that too. I'm not saying that that's what everybody does, but I'm saying in this class, that's the kind way to go about doing things. All right, is to let the reader know you're using L'Hopital's rule, and you do that with an h over the equal sign. But this will be the limit as x goes to 1 of, okay, the derivative of natural log of x, the derivative of the top is 1 over x. And the derivative of x minus 1 is going to be 1 minus 0. I wrote it out very explicitly here so you can see what I'm doing, but typically you would just do 1 over x over 1. And this is just the limit as x goes to 1 of 1 over x. And now we can actually take this limit. This limit is simply 1. Okay. Now, you know, you might be wondering where this comes from, or why this works. I mean, and we can't even really verify. We don't have a nice way to verify this. So to verify, let's try it with the other limit we know how to do. All right, so we're going to verify with x squared minus 1 over x minus 1, the limit as x goes to 1. We already know what this should go to. We did that at the beginning of the lecture. This should go to 1. Okay, so if we use L'Hopital's rule, right, we have the limit as x goes to 1 of, it will be 2x, okay, all over 1. Now I think I misspoke just then. It should actually go to 2, right? Because this will be 2 times 1 over 1, which is 2. And I believe that is what we got up here. Yes, it is. So I did misstate that. So using the factor and cancel method, we get 2. And using the L'Hopital's rule, we also get 2. So hopefully that helps verify. Okay, and to give another sort of explanation of why this works, let's start with this limit that we take it to, the limit as x goes to a. Now this doesn't count as a proof because there are plenty of things that can be wrong with this, but this I think gives a nice little way to show one of the reasons why this works. one special case. But let's say this limit exists, right? If the limit as x goes to a of f prime of x over g prime of x, if that's continuous, if both of these are continuous at this step and everything's nice, then this would be f prime of a over g prime of a. Okay. And if we go to the definition of this limit here, this is the limit, and I'm going to the x going to a version, right? So this is the limit as x goes to a of f of x minus f of a all over x minus a. And g prime of a would be the limit as x goes to a of g of x minus g of a all over x minus a. Okay. Now we can use our limit rules to bring that limit sign out to be the limit as x goes to a, and we can actually invert and multiply this guy so that it's f of x minus f of a all over x minus a times x minus a all over g of x minus g of a. And the x of a's are going to cancel, and then we'll be left with the limit as x goes to a of f of x minus f of a all over g of x minus g of a. And we're basically a step away, because the problem we had, the reason we needed to use LHopitals rule is because the limit as x goes to a of f of x over g of x was 0 over 0. So when we plugged a into f and g, we got f of a over g of a, which was 0 over 0. So f of a is 0, and g of a is 0. So we actually end up getting that this is equal to the limit as x goes to a of f of x over g of x. Okay, so we can trace that all the way back to here. And again, this is only a very, very special case. This doesn't count as a proof, but basically, taking the limit of the derivative, or the definition of the derivative, we can get back to what we originally started with. So that's sort of a semi-proof to where LHopitals rule comes from, okay, and why it works. Okay, so from here, let's look at some more examples. All right, so let's go. All right, here's an example. We should all know what this one is. The limit as x goes to 0 of sine of x over x. That's one of our special trig limits, right? And that goes to 1. But let's actually use LHopitals rule to give another explanation for why that is true, or more verification for why it's true. So basically, if we plug in sine of 0 is 0, then we have 0. So this is definitely a 0 over 0 case, so we can use LHopitals rule. So we get cosine x, derivative of the top, over the derivative of the bottom. So we have the limit as x goes to 0 of cosine of x. And plugging in 0, we get cosine of 0, which is 1. It's that simple. All right, but I will say this only works if you have a 0 over 0 case. All right, so remember, this only works for indeterminate forms, and I'll just say 0 over 0 and infinity over infinity. And there are a couple other cases it works for, but these are the two main cases. Because all the other cases, we actually work it into being a case of this type. Right, so for example, if I did the limit as x goes to 1 of x squared minus 1 over x plus 1. Right, this looks very similar to what we started with today, but this is not an indeterminate form, right? We get the limit as x goes to 1, if we get 1 minus 1 on the top, so we get 0 over 2. Right, so this is 0 over 2, which ends up being 0. But if you tried to use LHopitals rule, right, limit as x goes to 1 of x squared minus 1 over x plus 1, trying to use LHopitals rule, Right? So you get 2x over 1. If you plug that in, now if you plugged in 1, you'd get 2. Right? So this was not an indeterminate form. It's one of those where you can just plug and chug. That was one where you won't even have to factor and cancel. Back in chapter 2, you could just plug in the value and move on. All right, so keep that in mind. Always check when you're doing a limit. Don't just blindly do LHopitals rule. Check to make sure you can actually use it. Okay, so here's another example, a prime example of what LHopitals rule was developed for. Things like e to the x, where we can't factor anything out of this. We can't deal with this in any sort of normal way. We have to use LHopitals rule. And let's just double check to make sure that this is an indeterminate form. When you plug in 0, you get e to the 0, which is 1, minus 0 minus 1. So 1 minus 1, which is 0, over 0 squared. So this is a 0 over 0 case. Okay. Now, seem like things want to focus here, but from here we're going to use LHopitals rule, right? So this will be the limit as x goes to 0. You still have to write your limit signs. Okay, don't ever forget to do that. People still are. Okay, I'm still taking off for that. But the derivative of the top is going to be e to the x minus 1. And the derivative of the bottom is going to be 2x. Okay, so now let's try plugging things in. If I plug in 0, I get e to the 0, which is 1, minus 1, which is still 0. And in the bottom, you plug in 0, you get 0 again. So this is still an indeterminate form. Okay, so still a 0 over 0 case. But that's okay. We can just use LHopitals rule again because it's differentiable and nice and continuous and everything. So we'll just apply LHopitals rule again and get the limit as x goes to 0. The derivative of the top is e to the x over the derivative of the bottom, which is 2. And now we can plug and chug. If you plug in 0, you get e to the 0 over 2, which is 1/2. So this is an example to show that you can keep applying LHopitals rule. Just keep applying it as many times as you can or need to get down to finally something that works. Now, careful, because if you don't stop here, if you try to do it again, say in another step here, applying LHopitals rule again, first of all, is wrong because this is not a 0 over 0 case, but if you did, you'd get the limit as x goes to 0 of e to the x over 0, which is a big, nasty, horrible mess. Okay, so you don't want to, have that problem. Okay, you don't want to. You need to know when to stop, and that's when you can plug in a number and not get 0 over 0. Okay. All right, let's actually look at an infinity case. Here we have the limit as x goes to infinity of 2x cubed minus 2x plus 1 all over 3x cubed plus 3x squared minus 1. So when x is going to infinity, both the top and the bottom are going to infinity, and that's actually one of our indeterminate forms that we've talked about a lot. So what we did before, back in chapter 2, is we just said that this is the limit as x goes to infinity of the leading terms, right? This would be 2x cubed over 3x cubed. This is a nice trick that tends to work. In a couple cases where it doesn't, you have to be really careful about, but for the most part, this gives us that the limit is 2/3. But if you look up the LHopitals rule, what you'll find is that it says it works for infinity over infinity cases, right? Since this is an infinity over infinity case, LHopitals rule should apply. So down here, if we start using the LHopitals rule, or I should say LHopitals rule, not the LHopitals rule, but if we start using it, right, derivative of the top over the derivative of the bottom, so it'd be the limit as x goes to infinity of 6x squared minus 2 all over 9x squared plus 6x. Okay. And then check it now, but when we put in infinities here, we get infinity over infinity again. This is once again infinity over infinity. Okay, so if we use LHopitals rule again, we get the limit as x goes to infinity of 12x all over 18x plus 6. Okay, and once again, this is, if we plug in our infinities, which we're not really plugging in, but as x goes to infinity, we have this going to infinity over infinity. So if we were to apply LHopitals rule one more time, okay, we get the limit as x goes to infinity of 12 over 18, which ends up being 12 over 18, but specifically 2 over 3. Okay, so we do get the same answer, except it took a lot longer to get there, didn't it? Right here, this was much faster. Here, LHopitals rule is not actually the nicest way to go, but it does show that it does work for infinite cases, right? For examples where you have infinity over infinity, right? So let's actually apply it to an example where we can't use, say, one of our methods from chapter 2. All right, for example, say we have the limit as x goes to infinity of e to the 3x plus x all over the natural log of x. Well, we can't really do a leading terms trick because, well, what's our leading term of x? Well, the highest power of x we see here is 1, but e to the x will actually be going to infinity faster than x. So that's technically our leading term. And in the denominator we have natural log of x. So if you do this enough times, you'll start to know where this should be going. Looking at it, my conjecture is that it goes to infinity just from knowing what I know about transcendental functions, but say you didn't, all right? So this is definitely infinity over infinity, since as x goes to infinity, e to the stuff goes to infinity, x goes to infinity, natural log of x goes to infinity. So this is an infinity over infinity case. Therefore, we can use LHopitals rule. Okay, so using LHopitals rule, we'll have that this is the limit as x goes to infinity of derivative of the top, which will be 3 e to the 3x plus 1 all over the derivative of the bottom, which is 1 over x. Okay, now you could start trying to look at, what's going on, because as x goes to infinity, the denominator goes to 0. Numerator goes to infinity, infinity over 0. That's not as easy to deal with than if you just simplify this, right? You're dividing by a fraction, so you can invert and multiply. This is the limit as x goes to infinity of 3 e to the 3x plus 1 times x. And now I think it is a lot easier to see what's going on, because basically as x goes to infinity, we have e to the 3x going to infinity. That plus 1 is not changing anything, so we have infinity. And then x is going to infinity. So this is an infinity times infinity case, which is not indeterminate. Infinity times infinity is most assuredly infinity, and so that is our answer. Okay? And that is what I suspected from the fact that I know e to the x goes to infinity faster than anything else does. But we have used the LHopitals rule here to prove it. all right, to confirm our suspicions. Okay, let's try another example. Let's say we have the limit as x goes to infinity of the natural log of x over x squared plus 2x. Okay. Well, as x goes to infinity, so does the natural log of x, and so does x squared plus 2x. Okay. So since this is infinity over infinity, we can use LHopitals Rule, which will be the limit as x goes to infinity. Let's shift this down a little bit. Now the derivative of the top, which is 1 over x, all over the derivative of the bottom, which is 2x plus 2. Okay. Now, once again, this is a case where it's actually a little easier to simplify things first, because now we have the numerator going to 0, the denominator going to infinity, 0 over infinity. Some of you may not be very savvy with infinities and how they work well enough to, be able to tell what that's going to. So just treat this as a fraction over a fraction, invert and multiply. Okay, so that you have 1 over x times 1 over 2x plus 2. You can treat this like a product instead of a fraction. Okay, and so you have 1 over x, that goes to 0 as x goes to infinity. And then you have 1 over 2x plus 2, so you have the denominator going to infinity, and 1 on the top, so constant over infinity, so this whole thing goes to 0. So you basically have 0 times 0, which is 0. So if you were curious, 0 over infinity, well, actually I should be very careful about that. But typically 0 over infinity, 0 over infinity is going to be 0, because mainly what we're doing is saying that it's 0 times 1 over infinity, and 1 over infinity is 0. Okay, so this is not ever anything you would write on formal work, but it's something you can keep in your head to help you keep things straight. All right? And I actually guessed that this would be 0 because ln goes slower to infinity than does x squared. Okay? And if you were ever curious why we call it an indeterminate form, because, well, there's lots of different cases. For example, here was a case that we looked at earlier that was an infinity over infinity case that equaled 2/3, right? It gave us some number. Here was an infinity over infinity case that gave us infinity. And then here was an infinity over infinity case that gave us 0. Okay, and you can actually set up problems where your infinity over infinity gives you whatever you want. It can give you infinity, it can give you 0, it can give you 1, it can give you 2/3. There are many, many cases. So that's why infinity over infinity is an indeterminate case, as is 0 over 0. 0 over 0 is the same way. Sometimes it gives you 1, sometimes it gives you 0, sometimes it gives you infinity. Right? It's just depending on what's going on, what has happened. Okay. All right, there's another big indeterminate form that LHopitals Rule can apply to, and that's the 0 times infinity case. Now you might be thinking, well, isn't that just 0? The answer is no. And that's because, well, if whatever is going to 0 goes to 0 faster than whatever is going to infinity, then the whole thing will go to 0. But if the thing going to infinity goes to infinity faster, okay, then the thing going to 0, then the whole thing will go to infinity, and they might actually cancel each other out. Okay, so the trick to these, though, right? The trick here is always rewrite the problem to be a 0 over 0 or infinity over infinity case, right? So you're just going to use some algebra to rewrite things so that it's a case that LHopitals rule can apply to. Okay? Let's start by looking at a pretty simple example here. As x goes to infinity, we're looking at that limit as of x squared times e to the negative x. So x squared, that goes to infinity as x goes to infinity, obviously. All right, x goes to infinity, infinity squared is infinity. E to the negative x, on the other hand, goes to 0. Right? E to the negative x, so e to the negative infinity is basically 0. So this is a 0 times infinity case. So what we're going to do is rewrite this problem so that it's 0 over 0 or infinity over infinity. And we're basically going to do this sort of idea in every problem like this. I'm just going to rewrite this e to the negative x as, well, that negative power I can bring down underneath a fraction like this. So it's x squared over e to the x. Okay. Now it's an infinity over infinity case, right? Because as x goes to infinity, x squared goes to infinity, and e to the x goes to infinity. So now we can apply LHopitals rule, right, to get the limit as x goes to infinity of 2x over e to the x. Okay, it's still infinity over infinity though, right, because 2x will also go to infinity. So now this is, we'll use LHopitals rule again to give me the limit as x goes to infinity of 2 over e to the x. Okay, so now the numerator is just 2, and the denominator is going to infinity, so the whole thing goes to 0. Okay. So there we go. There's one case where a 0 times infinity gives us 0. Let's look at another example. Okay, this one's a little more complicated. We have the limit as x goes to 0 from the right of x times the natural log of x squared. Okay. Again, LHopitals rule will work just fine with right or left side limits, but basically we have x is going to 0. I'll use a different color for this. X is going to 0. As x goes to 0 from the right, x goes to 0 from the right. Okay. As x goes to 0 from the right here, I have 0 squared on the inside of natural log. So that, if you remember what natural log looks like that basically, and at 0, so this is just natural log of x, but basically as x goes to 0, natural log goes to negative infinity from the right. Okay, and you can't see any of that, can you? Okay. So that means that as x goes to 0 from the right, natural log of x squared, this whole thing, is going to negative infinity. So this is a 0 times infinity case. All right. Now we are going to rewrite this problem in a way that's more manageable. And how we're going to do that, all right, is you always move something down into the denominator. We don't have a denominator here. To use LHopitals rule, you have to have a fraction. So we're going to move something down into the fraction. And the easiest way to do that is the x. We just move whatever's the easiest thing to move. So the x is the easiest to move, so that's what we're going to do. This will be natural log of x squared all over x to the negative 1. All right, so now we can use LHopitals rule. And actually, before I do that, there's one more thing we can do here. right? This is the limit as x goes to 0 from the right. I'm going to move that 2 out since I have that x squared. That'll make the derivative easier to take. Okay. All right, so now I will apply LHopitals Rule, since now what I have is as x goes to 0 from the right, this is going to negative infinity. Okay, and this, it's harder to see, but this is 1 over x, right? And 1 over x is x goes to 0, this thing goes to positive infinity. So now we have a infinity over infinity case. So we can apply LHopitals Rule, which says that this will be 2 over x all over negative x minus 2. Okay. And now that I'm here, I'm actually going to bring this back up. Usually that's what you want to do, is you bring it back up to simplify from the right. So I have 2 over x times, I'll bring the negative along with it, times x squared. I bring that up, so that will cancel there. So I get the limit as x goes to 0 from the right of negative 2x. And the whole thing now is just going to be 0. Okay. So these end up being a little more complicated, but as long as you take it slow, do things carefully, you should be okay. Okay, so let's look at another example. Okay, so now we have the limit as x goes to infinity of x squared times sine of 1 over x. All right, so first of all, as x goes to infinity, x squared is going to infinity. Okay, and as x goes to infinity, 1 over x, what's in here, goes to 0, and sine of 0 is 0. So this whole thing goes to 0. Okay, so this is 0 times infinity. So let's rewrite it. We always do it by just moving something into the denominator, whatever is the easiest thing to move into the denominator. And I'm going to do x squared. And one thing I'm also going to do, this is just going to simplify things a little bit, is I'm going to rewrite this thing as x to the negative 2 on the inside of sine. Okay. All right, so now we should have a 0 over 0 or infinity over infinity. You can think of this problem as either sine of x to the negative 2 or sine of 1 over x squared over 1 over x squared. Whichever is more comfortable for you, because as x goes to infinity, 1 over x squared goes to 0. So the bottom goes to 0, the top goes to 0. This is a 0 over 0 case. Okay, that might be a little harder to see here, but it'd be a little easier to take the derivative here. Okay, so what we're basically going to get is taking or using LHopitals Rule. I'll get the limit as x goes to infinity of, right, be the derivative cosine of x to the negative 2 times, now the derivative of the stuff, which will be negative 2, x to the negative 3, all over, now the derivative of the bottom, which will be negative 2, x to the negative 3. Now here's the nice thing about this. Check that out. We have the same thing on the top and the bottom. They both cancel. And so we're essentially just left with the limit as x goes to infinity of cosine of x to the negative 2. Okay, which is the limit as x goes to infinity of cosine of 1 over x squared. And as x goes to infinity, this thing goes to 0. So the whole thing is going to be cosine of 0, which is 1. Right, a bit more work, these examples. Okay. Yeah, but it does let us deal with limits that were a lot harder to deal with before. Now we actually can. I will say that if you were kind of clever, you probably already saw something we could do here without having to use LHopitals Rule. Okay, because we have sign of stuff over the same exact stuff. On this step, if we had, I don't know, maybe let b equal 1 over x squared, then I would have, if I rewrote this limit, I'd have the limit as b goes to, and I'll talk about that in just a second, sine of b over b. Now, as x goes to infinity, 1 over x squared, okay, so 1 over x squared goes to 0 as x goes to infinity. So that means that b goes to 0 as x goes to infinity. So we could rewrite this limit as b goes to 0 of sine of b over b, and the limit of sine of b over b as b goes to 0, that's one of our famous trig limits, 1. So we could have actually done that instead of using LHopitals Rule. Okay, kind of tricky, but if you saw that pattern, that is something you could do for this problem. Okay, one last thing I really want to mention here is that you still need to know how to use limit ideas from before, because they're not always, you're not always going to be able to use LHopitals Rule, right? So LHopitals Rule won't always work. Most people think it will, and in most cases it will, but often it will fall apart on you. For example, if I have the limit as x goes to infinity, and I want to, let's say it's the square root of x plus 1 all over x. Okay, so this is definitely an infinity over infinity case, because as x goes to infinity, x squared goes to infinity, despite the fact that it's being stuck under a square root, and so does x. So since this is an infinity over infinity case, we're going to take the derivative of the top and the bottom, so, or we can use LHopitals Rule, in other words. So let's actually simplify this a bit so we can get started. It's going to be a chain rule. So the derivative of the top is 1/2 times x squared plus 1 to the negative 1/2, then times the derivative of the inside, which will be 2x, okay, which the 2 cancels here, all over the derivative of the bottom, which is 1. Okay, so I have x here, and I'm just going to move this down here. So I have the limit as x goes to infinity of x over x squared plus 1 to the 1/2. And I'm left with basically, does everyone see that I'm basically left with just what I started with but flipped over? Yeah, so we've kind of done nothing. And if you try to do it again, this is still infinity over infinity. Doing it again, the same steps, you'll actually get 1 over 1/2 times x squared plus 1 to the negative 1/2 times 2x. Once again, now we can move this guy up, right, because we have it to the negative 1/2, and we'll have the limit as x goes to infinity of x squared plus 1 to the 1/2 all over x, which is the limit as x goes to infinity of the square root of x plus 1 all over x. Kind of problematic, because now we're right back to where we started with. So we actually have to use leading term idea for this one, right? So the limit as x goes to infinity, since everything is positive and whatnot, what I can do, this thing will be defined So I can move this on the inside and get this is the square root, the limit as x goes to infinity of x squared plus 1. That's how we're going to do this one. All over the limit as x goes to infinity of x. Okay? And the reason I brought this inside like this is because the leading term is all that matters. So this is actually going to be the square root of the limit of just x squared. Right? This is by the leading term idea, because only the x squared is going to matter eventually. And then if we move the limits back outside, what we have is the limit as x goes to infinity of the square root of x squared all over x. Okay, and since we're going to positive infinity, what this means is that we have the limit as x goes to infinity of this is just going to be x over x. So the whole thing goes to 1. Okay, so we have to use some of our previous rules to do this one, as LHopitals Rule will actually fail us here. Okay, so that's about all I really want to say about LHopitals Rule. In my experience, students seem to love it. It's a great way to look at limits, calculate them, and in some cases faster than before. But be careful because they won't always work, and don't try to use it when you can't. Okay, so that's it. Cheers.